Pleasant day to everyone. Today we're going to discuss part 6 of module 6 of subject CE3151, fitting curves and interpolation. In this lecture, we're going to discuss one of the interpolation methods for polynomials, which is forward Gregory-Newton. The forward Gregory-Newton method is an approximation using regular x intervals. The required function of x would fall under the first half of the data points, and the closest approximation of the function of x is taken from the forward-leading differences. It is likewise possible to use a value preceding the required as x sub o only if the difference table would close to 0. Else, if the difference table ends unsymmetrically, meaning that the last delta will not equate to 0, we have to revert back in interpolation using the x sub o of the given table or given dataset. Given the data points, the conditions for forward Gregory-Newton would be as follows. Given now the set of x, the differences of h, or the values of h, which is the difference of the values of x, or the intervals of x, should be constant or should be equal. And for the function of x, this would be found before the midline of the data set. The formula for interpolation for forward Gregory-Newton would be defined as f of x is identical to the function of x sub o plus r sub h, wherein the equation f of x sub o plus rh is equal to y sub o plus r times delta y sub o plus r times r minus 1 all over 2 factorial times the second difference of y sub o plus r times r minus 1 times r minus 2 all over 3 factorial times the third difference of y sub o. And if you are going to observe, there is a pattern for the equation. The value of r is computed as x minus x sub o all over h. And take note that for y sub o, delta y sub o, delta squared y sub o, delta 3y sub o is the leading forward differences of our finite difference table. So to understand forward Gregory-Newton, let us solve some examples. So for example 1, determine the function of x for x equal to 3.5 given the following data set. So first, we tabulate our answer and determine delta y sub o, which is computed as negative 4 minus negative 22, giving us 18. 19 minus negative 4 is 23. 47 minus 19 is 28. And then next, we solve for the delta squared of y sub o, and that is 23 minus 18, and 28 minus 23, which is 5. And we solve for delta cube y sub o, which is equal to 0. So from here, we use now the values, or the first values, for our forward differences. So the leading differences is negative 22, 18, 5, and 0. So next, we solve for the value of each. And from the table, we could see that all differences of our x is equal to 3. So next, we solve now for the value of r. And that's equal to x minus x sub o all over h. So x now is 3.5. X sub o is 3. H is 3, giving us a value of r equal to 0.1667. And applying now our general formula for the forward Gregory-Newton. So f of x is now equal to y sub o plus r. delta y sub o plus r times r minus 1 all over 2 factorial times delta squared y sub o, and so on. So we have substitute all the values of our y and deltas. So f of x is equal to negative 22 plus r 0.1667 times 18 plus 0.1667 times 0.1667 minus 1 all over 2 factorial times delta cube y sub o, which is equal to 5. So since delta cube is 0, so we could simplify our fourth term as 0. So simplifying now, we get the function of x, wherein x is equal to 3.5, will give us a value of negative 19.346678. Okay, so we have another example for the given data set of x and y. Determine the function of x when x is equal to 3.5. So again, we tabulate our answer or our solution for x and y in order to solve for the following deltas. So we have delta y sub o, and that is solved as negative 3 minus negative 7, giving us 4. 6 minus negative 3 is 9. 25 minus 6 is 19. 62 minus 25 is 37. And 129 minus 62 is 67. And then from here, we solve now for delta squared y sub o. That is now 9 minus 4 is equal to 5. 19 minus 9 is 10. 37 minus 19 is 18. 67 minus 37 is 30. So next, we solve for delta cube y sub o. And that's 10 minus 5 is 5. 18 minus 10 is 8. 30 minus 18 is 12. Followed by negative delta raised to 4 y sub o. That's equal now to 3, 4. And we get delta raised to 5 y sub o, which is equal to 1. So we stop at delta raised to 5 y sub o since we do not have any terms that we could get the difference. So we take our leading forward difference as negative 7, 4, 5, 5, 3, 1 for the values of y until delta raised to 5y sub o. So next step is to determine the value of each or the differences between our x's or the interval between the values of x, which is equal to 1 for all values of x. And then we can now solve for the value of r, which is x minus x sub o all over h. In this case, x is equal to 3.5, and x sub o is the first value of x in our data set, which is 2. Therefore, r now is equal to 3.5 minus 2 divided by 1, which is now equal to 1.5. So given now the values of h are 1, y sub o, until delta y sub o raised to 5. So we can now apply these values in the equation of f of x equal to y sub o plus r times delta y sub o plus r times r minus 1 over 2 factorial times delta squared y sub o, and so on. So for here, we will now get negative 7 plus 1.5 times 4 plus 1.5 times 1.5 minus 1 all over 2 factorial times 5 plus 1.5 times 1.5 minus 1 times 1.5 minus 2 all over 3 factorial times 5 plus 1.5 times 1.5 minus 1 times 1.5 minus 2 times 1.5 minus 3 all over 4 factorial times 3 plus 1.5 times 1.5 minus 1 times 1.5 minus 2 times 1.5 minus 3 times 1.5 minus 4 all over 5 factorial times delta raised to 5 sub o, which is equal to 1. So simplifying this equation, we get now the function of x equal to 3.5 is equal to 0.6210937.5. So for the given data set, solve now example number 3. So we solve now for the function of x when x is equal to 2.5. Again, we first determine our forward differences using our table. So we get delta y sub o as 83 minus 15 equal to 68. 519 minus 83 is 436. 1659 minus 519 is 1140. 3839 minus 1659 is equal to 2001. 7395 minus 3839 is equal to 3556. And then we solve for delta squared y sub o, and that's equal to 436 minus 68 gives us 368. 1140 minus 436 gives us 704. 180 minus 1140 gives us 1040. And 3,556 minus 180 gives us 1376. Next, we solve for delta cube y sub o, which gives us 704 minus 368 equal to 336. 1040 minus 704 gives us 336. 1376 minus 1040 gives us 336. Solving now for delta raised to 4y sub o is giving us a value of 0. So since our difference now have close to 0, we stop at delta raised to 4y sub o. So once we have solved for your forward differences, we now solve for our h value, which is equal to 1. And from here, we can now solve for our r based on the first point, which is x sub o equal to 1 with y equal to 15. So from here, we now solve r is equal to x is 2.5 minus x sub o is 1. H is 1. So therefore, r now is equal to 1.5. So substituting the value of r and the value of our leading forward differences, we can now solve for the function of x as y sub o 15 plus 1.5 times 68 plus 1.5 times 1.5 minus 1 all over 2 factorial times 368 plus 1.5 times 1.5 minus 1 multiplied to 1.5 minus 2 all over 3 factorial times 336 plus 1.5 times 1.5 minus 1 times 1.5 minus 2 times 1.5 minus 3 all over 4 factorial times delta raised to 4 y sub o, which is equal to 0. So simplifying this equation, we get the function of x equal to 2.5 is equal to 15 plus 102 plus 138 minus 21 plus 0, or f of 2.5 now is equal to 234. Another way of solving example number 3 is basing our x sub o on the preceding point x equal to 2. So r now will be computed as x minus x sub o over h. Still have the same formula, but instead of using the first value of x, we use the second value, which is 2, which will give us a value of 0.5. And in this case, since we are basing our answer on the preceding point x sub o, or the preceding point of x sub o, which is 2, we now start off our solution with the values under this values or this table. So we have now 83, 436, 704 336, and 0 as the values of y sub o, delta y sub o, delta squared y sub o, delta cube y sub o, and delta raised to 4y sub o. So, substituting the values now of r, 0.5, and the highlighted or the enclosed values of y and delta y's, we now get f of x is equal to 83 plus 0.5 times 436 plus 0.5 times 0.5 minus 1 times 704 plus 0.5 times 0.5 minus 1 times 0.5 minus 2 all over 3 factorial times 336 plus 0 will now give us function of 2.5 is equal to 83 plus 218 minus 88 plus 21, which is also equal to 234. So this example number 3 proves that we could use the second or another set of leading or forward differences in our solution if our closing value for our table is equal to 0. And then, since we are solving for a value of x equal to 2.5, which is between 2 and 3, we could use the values of 8, 3, 436, 704, 336, with likewise 519, 114, 10, 40, and 336. So next example, number 4, we determine now the function of x for x equal to 1.2 for the following data set. So again, we first identify our forward differences. So for delta y sub o, we get 7.1 minus 5.1 is 2. 8 minus 7.1 is 0.9. 8.1 minus 8 is 0.1. And 7.8 minus 8.1 is negative 0.3. Next, we have delta squared y sub o, which is equal now to 0.9 minus 2, which is negative 1.1. 0.1 minus 0.9, which is negative 0.8, and negative 0.3 minus 0.1, which gives us negative 0.4. Next, we solve for delta cube y sub o as negative 0.8 minus negative 1.1, giving us 0.3, negative 4.4 minus 0. Or negative 0.8, which gives us 0.4. Wherein delta raised to 4 y sub o now yields a value of 0.1. So for our solution, we have our leading forward difference of 5.1, 2, negative 1.1, 0.3, and 0.1 for the values of y sub o and the delta values. So next, we solve for h, and we could check that for all values of x, it is equal to 0.6. So basing now our answer or our solution with our first entry, which is 0.4, we have r is equal to x minus x sub o all over h, wherein x is equal to 1.2, x sub o, which is the first value of x, is 0.4. So divided by h is equal to 0.6. So we get a value of 4 over 3 for r. So based now on the preceding point, x sub o is equal to 0.4. So we get now the function of x as y sub o 5.1 plus 4 over 3 times 2 plus 4 over 3 times 4 over 3 minus 1 all over 2 factorial times negative 1.1 plus 4 over 3 times 4 over 3 minus 1 times 4 over 3 minus 2 all over 3 factorial times 0.3 plus 4 over 3 times 4 over 3 minus 1 multiplied to 4 over 3 minus 2 times 4 over 3 minus 3 all over 4 factorial times delta raised to 4 y sub o, which is equal to 0.1. So simplifying these values, we get function of x equal to 1.2 is equal to 5.1 plus 2.667 minus 0.2444 minus 0.0181 480.002056. Or the function of x equal to 1.2 is now equal to 7.5094648. So if you're going to notice the value of the function of x or of y when x is equal to 1.2 is 7.5, and it is in between 7.1 and 8, as 1.2 is between 1 and 1.6. So if we are going to solve example number 4 using the preceding or succeeding point as our x sub o, wherein we use now 1, r now can be computed as 1.2 minus 1 all over 0.6, or that will give us a value of 4 over 3. So using our finite differences table, we'll now be using the values for y and the deltas using 7.1, 0.9, negative 0.8, and 0.4. So substituting these values and r in our equation for forward Gregory Newton, we will have f of x is equal to 7.1 plus 4 over 3 times 0.9 plus 4 over 3 times 4 over 3 minus 1 all over 2 factorial times negative 0.8 plus 4 over 3 times 4 over 3 minus 1 times 4 over 3 minus 2 all over 3 factorial times 0.4, which will give us now a value of the function of 1.2 is equal to 7.335803. So if we're going to compare this value with the value of f of x in our previous solution, this is not equal to 7.5094648, which concludes or verifies that we cannot use the other values of y and the deltas for our solution for the function of x if our closing value is not equal to 0. Again, it is only applicable to use the other values of your forward differences if our closing value or the table closes at 0. So this is it for forward Gregory Newton method. We'll be discussing the other method in the next video lectures. Thank you for listening.